Here's a little Unit 3 review as you're making your final preparations for your Unit 3 test on solutions and gas laws. All right, so as you learn about the gas laws, of course, the first thing you need to be aware of is that we have solids, liquids, and gases because of the balance between the intermolecular forces. Those are things like the London dispersion forces, which are the temporary forces, the dipole-dipole forces, and the hydrogen bonding. And we have a balance between those intermolecular forces and the amount of kinetic energy that the particles have. So which state has the greatest intermolecular force? Hopefully you were thinking the solids. And so the stronger the intermolecular force, the higher the boiling point or melting point would be. Solids have strong intermolecular forces, and that's what keeps them there. So that's the greatest factor that affects especially boiling. Of course, these different solids, liquids, and gases would have been the same at room temperature. The lowest intermolecular force, of course, would be the gas, and in a perfect world, those gas particles would have no intermolecular attractions. And so these would be more likely your nonpolar molecules, or possibly some of the diatomic molecules that, of course, would be nonpolar. So they would have the weakest intermolecular forces of hydrogen bonding. All right, now take a moment. This may be a great time to get out your periodic table, pause the video, and see if you can figure out what intermolecular force is present, or the strongest intermolecular force that is present. So first molecule to disappear was O2. So hopefully as you're thinking about O2, and there's CH4, there's PCl3. Hopefully you were thinking O2, that's going to be London dispersion forces. Of course, that O2 is non-polar. PCl3, this is going to be a dipole-dipole, is our intermolecular force. And CH4 would also have London dispersion forces. So if we were to take a look at those and see which one would evaporate at the lowest temperature, it would be your London dispersion forces, and in this case your O2, because it is your smallest molecule. The intermolecular forces that are stronger, the dipole-dipole and PCl3, would keep those molecules together in the liquid or solid state and make them evaporate at or boil at a higher temperature. And again, in order to figure this out, we're looking at the electronegativity difference and the shape of the molecule. All right, you also need to know the different types of solids, okay? So this is a diamond, so we've got carbon atoms repeating over and over and over again. Hopefully you were thinking that's a network. How about this solid? Hopefully you're thinking that's metallic, like a sheet of aluminum, for example. Remember, of course, that metals don't hold on to their electrons, so you can see the electrons kind of running everywhere with the nuclei present. How about this solid? Hopefully you were thinking this is an ionic solid. We've got our positive ions and our negative ions. Hopefully you were thinking CO2. It's a covalent or a molecular solid because we've got two nonmetals. You also need to know about the phase change diagram. Now, I like this phase change diagram because you can see where 1 atmosphere of pressure is. And so you need to know A, B, and C. Hopefully you're thinking A is a solid, B is a liquid, and C is a gas. And you are exactly right. You also need to know what happens when you go from A to B, A to C, C to B, for example. Actually, all of them. So take a moment and think about that. This, again, is a great time to pause the video. Hopefully you were thinking from A to B, that's melting from when a solid goes to a liquid. A to C, that's a solid to a gas right here. that would be sublimation. And C to B, hopefully you were thinking condensation. That's our gas to our liquid. You need to know where the critical point is. So hopefully you were thinking right there. And you also need to know the triple point, which is right there. What property is shown here? So we have some particles. And hopefully you're thinking, wow, those particles can be compressed. And you are exactly right. Particles, especially of a gas, are easily compressed. Solids and liquids, not so much. Not at all, actually. All right, what about this property of a gas? So we've got some gas particles there in red. And so as you can see, they're spreading out or they're diffusing. That is one of the properties of gases. How about this one? Well, this one's trying to show pressure because you can see the particles banging into the sides of their containers, and that's what causes pressure. And you know all the different ways that we measure pressure. And you need to be able to convert them. So great time to pause the video and see what you can do. Hopefully you started with what was given and then use the correct conversion. That 760 millimeters of mercury is 14.7 pounds per square inch. And you came up with 14.1 pounds per square inch. When you're converting with atmospheres, again, you're starting with the given. And hopefully you came up with about 0.961 pounds or atmospheres. Notice we've rounded that to 3 significant figures because that's what we're given in the problem. All right? Take a moment and take a look at this problem. See if you can solve it. Another great time to pause the video. Of course, hopefully you were thinking of Dalton's law of partial pressures here, because we have the pressures of various gases, and when they're added up, we can find the total pressure. The problem here is that our units are not the same. You see, we have millimeters, kilopascals, and atmospheres. You need to be able to recognize those as units of measure for pressure, and then, of course, simply convert. So I decided to convert everything to atmospheres because whenever I'm dealing with gases, I always convert to atmospheres. And so I get 0.7803 for the pressure of nitrogen. Then I do the same thing with our kilopascals from oxygen, convert those to atmospheres using my dimensional analysis. I've already got my other gases present. I simply add those all together to get a total atmospheric pressure of 1.000. And I should have probably rounded that to 3 significant figures based on the measurements here. So it shouldn't be 4 significant figures here, just 3. All right. Don't forget that gases are standardized. We like to talk about those gases in terms of STP, standard temperature and pressure. Standard temperature and pressure are 0 degrees Celsius, and standard pressure is 1 atmosphere. Don't forget that at STP, 1 mole of a gas is 22.4 liters of a gas, of any gas. All right. So what would you say the mass of helium in a round balloon at STP that has 6.25 liters of helium? And this is a great time to pause the video, a simple dimensional analysis problem. So how did you do? Hopefully you started with the given as always. And then for this one, all you had to do was use that conversion that 22.4 liters is 1 mole. And then to convert to grams using your molar mass. And so you came up with, 1.12 grams of helium. You could have probably kept that with 4 significant figures, because now that I'm taking a look at this, I see I have 4 significant figures here, and I should have kept that at 4 significant figures. You also need to be able to recognize the gas laws. So take a moment and see if you can recognize each of these. All right, so what'd you say for the first one? Constant volume, TP. Hopefully you were thinking Gay-Lussac's law. For the second one, constant temperature, pressure, and volume are changing. So Boyle's law. Volume, temperature, and pressure all related. That's our combined gas law, which you will need to know those gas laws. I will give you the pressure conversions, but you will need to know the laws. How about this next one? Pressure, temperature, and volume are all proportional at constant pressure, so T and V. So Charles's law. And the number of particles, of course, that's Avogadro's law. And the ideal gas law. So keep practicing those. Don't forget what R is. You will be given R as well, so you don't need to memorize R for the test. But you do need to be able to use each of these laws as well. And here's an opportunity for you to practice just that. So great time to pause the video. And once you take a look at all of your given pieces of information, of course, there's some you're not going to need, like the 20 miles above the surface. And I can see that we've got 2 temperatures, 2 pressures, and a volume. And we're asked to find our other volume. And so for this one, of course, we're going to be using, so you figure out what everything is, take all of your temperatures and convert to kelvins. And use your combined gas law. But you, of course, need to convert your pressure to atmospheres. When I'm dealing with that gases, and I've had lots of you ask me questions about this, I always go to volume in liters if possible. Naturally, temperature always has to be in kelvins. I always like to do pressure in atmospheres and volume in liters. The biggest thing you're trying to do is make sure your units cancel out. All right, and so we can take a look at that and then simply just plug it in and solve for V2. Now, in order to do that, I'm going to do 0.99 times 4.19 times 10 to the third liters divided by 295. Then I'm going to multiply 0.092 and 240, or divide those. And then I'm simply going to divide each side by 3.8 times 10 to the minus 4. I'm going to notice what units are going to cancel out so that I am left with liters, because I am looking for volume. So I do want to be left in units of liters. And then I'm going to simply round that to 2 significant figures because I believe somewhere right here, there you go, and that pressure right there, I have only 2 significant figures. And so there we go. All right, here's a quick little solution vocabulary review for you because the solution part of the test is very vocabulary heavy. So an opportunity for you to practice. So go ahead, let's get started. By the way, you do need to be able to look at this curve and pull information from it. All right, so what'd you say for number 1? Hopefully you said this is a super saturated solution. It's more than saturated because it's containing solute that is settling to the bottom. So probably what I would do with this solution, super saturated solution, is one that is unstable. So I will have heated it up to try to get the rest of that solute to dissolve. So I would say A, of course, is dilute. B, or C, I would say is saturated because I can see that we've got solute settling to the bottom, which tells me that it is saturated. And A and B are unsaturated. If I put any more solute in B and it settled to the bottom, then boom, I know that it's saturated. And that's really the way to find out. Hopefully you were saying that solution 1 has been heated up, obviously, to hold that excess solute. Solution 2, you can see the solute settling out. And solution 3 is a little bit more dilute. Hopefully you were thinking aqueous for number 6, AQ. Hopefully you were thinking that for a solid, typically solubility increases as temperature increases, and that works the opposite for a gas. All right, so how do we do this one? Well, the first thing I have to look for is I have to figure out, okay, so what chemical am I looking for here? And I figure potassium chloride, so I'm going to have to find that here. And then I'm going to look at 100 grams, 50 degrees Celsius. So then I'm going to go up to 50 degrees Celsius. And I can see that a little over 40, of course, if my lines were straight. And so that would be a super saturated solution. So that means that I would have to heat it up and really stir it to get that much potassium chloride, 50 grams, to dissolve. So what's happening here? We're diluting that solution. So don't forget, you can determine the concentration of the new solution if you just know the concentration and volume of the first solution. Because the thing that doesn't change here is the number of solute particles. And remember, when we're measuring molarity, that is the moles or the number of particles per liter. And you need to be familiar with these colligative properties. You need to know what they are, like boiling point elevation, freezing point depression, and vapor pressure reduction. Hopefully you were thinking that the solute is insoluble. The two liquids are immiscible. They must be different types of solutions, polar or nonpolar. You also will need to know about how we can measure the concentration of solution, mass volume percents, mass percents, and molarity. And so let's do a couple of practices. Another great time to pause the video so that you can practice on your own. All right, so let's check how you did. Hopefully you were thinking, okay, I've got to do a mass to mass percent here. So I need my masses. So I'm going to need my mass of sodium fluoride here. I'm given the mass to mass percent, and I know the mass of the toothpaste in the tube. So in order to solve for that, the first thing I'm going to need to do is turn that 24% into a decimal. So I'm going to move that decimal over twice to make 0.0024. Is the mass of NaF over 221. Then multiply each side by 221. And that's going to cancel out. Whoops. And so simply by having, and I'm sorry, I don't know why I don't have the answer here, 0.0024 times 221, I come up with 0.5304. So we are right at the legal limit of what is allowed. is what I get, 0.5304. And of course, if I'm going to round that for significant figures, I'm going to come right here. And that's how many grams of NAF are in our toothpaste, which is good because that is right at the allowable lethal dose, which is why we don't swallow our toothpaste. We spit it out. All right, let's try another one. How many liters of hydrogen at STP are required to produce 13.8 grams of ammonia? So how are you going to attack a problem like this? Hopefully, the first thing you're going to do is write your balanced equation. And then you're going to start with that 13.8 grams. So this is a great time to pause the video and see if you can do that. All right, how did you do? Hopefully, the first thing you did was convert your grams to moles, and then use the mole ratio from your balanced equation, and then figured out your liters of hydrogen using 1 mole is 22.4. Went straight across the top and multiplied, straight across the bottom and multiplied, and then divide. And you should come up with 27.3 rounded to 3 significant figures. You'll also need to be able to calculate molarity. This is a buffer used in hospitals for blood type issues. So if you were going to, what mass of that buffer would be needed to prepare a 500 milliliter solution, 3 molar solution? So take a moment, pause the video, see what you can do. Hopefully you remembered that molarity is your number of moles per liter. In this case, we've got volume and molarity. So volume times, and you just have to convert your volume to liters. And hopefully you know that molarity times volume is equal to the number of moles. And so you can easily come up with 1.5 moles of that buffer, and then use your molar mass to figure out the grams of Tris buffer needed. And that can be rounded to 4 significant figures. Here's another one for you to do. Because you now might need to take that buffer and dilute it down. So take a moment, pause the video, and see what you can do. All right, so how did you do? Hopefully you used this equation to start. And we're solving for M2 here. Oh, I'm sorry, we're solving for V2 here. All right, and so if I simply substitute everything into the problem, divide both sides by 3 molar, we should get 0.0371 liters is what we're going to need for volume 2. And so what we would need to do is take 37.1 milliliters of the buffer and dilute it down to add water to 53.0 milliliters. And that's how we would make that buffer. All right. Of course, solutions stoichiometry, you need to be able to do that as well. So take a moment and see if you can do this problem given that balanced chemical equation. All right, so let's take a look at how you did. Hopefully you looked at what you were given. We know it's STP, so 22.4 liters of a gas equals 1 mole. And hopefully you're starting with those liters. You can then convert your volume to moles. And then looking at your balanced equation, 2 moles of NaCl equals 1 mole of Cl2. And figure out how many moles of NaCl you need. And so we're trying to figure for volume there. So volume, of course, is your number of moles divided by your molarity. Notice that your moles are going to cancel here, top and bottom. And those leaders will flip right up top and round that to two significant figures for 2.0 times 10 to the 6th. All right, so if you've done all of the work for this unit, you should be ready for the test. And we'll be completing that test to Monday in class. If you have any questions, feel free to let me know.